So here I'd like to discuss one more concept. In algebra geometric correspondence that is not often discussed in presentations because it comes from so-called classical mathematics. And we are actually moving just a bit to quantum mathematics or to semi-classical mathematics. And while in classical mathematics, you are mostly interested in functions, in semi-classical mathematics, as you may know from mechanics in particular, functions are associated to so-called flows on the phase space. And this thing, namely unification of the notion of observable, that is a function, and dynamic, that is a vector field. So this unification becomes clear in quantum mechanics. In quantum mechanics, there is no difference. There is a difference in classical mechanics. However, all this physics I'll discuss on the physics hall. Here I just want to say that, believe me, it is important to discuss derivations. So, suppose we have a smooth manifold. We will consider smooth manifold as a prototype for algebra geometric constructions. And suppose we have V vector field. So, having a function and having a vector field, we can define a map F going to LV of F. So this is the Lie derivative. In coordinates, it's something like this. If you look at this definition, you will see that this definition is purely geometrical. You need to imagine smooth manifold X and the vector field. It means that to each point you have a tangent vector, okay? And if manifold has singularities, or if manifold is a scheme, like double point, triple point, you may think that this notion of vector field has no generalization. Okay? However, let us consider this geometrical notion algebraically. So what do we have? We have a map from the algebra to itself that I'll call D. With the property that D of A times B equals dA times B plus A times dB. So this is called the Leibniz rule. I'd like to remind you that it was called Leibniz rule Not because it was discovered by Leibniz. Actually, Leibniz had the wrong idea. Originally, Leibniz thought that DAB, okay, originally, is dA times dB. So you may think, how could it be that such a great scientist could make such a mistake? But he actually did. It was Newton who told him that actual formula is like this. Then Leibniz was impressed and started to tell everybody that this is not right, this is right. And since he was promoting this idea, everybody else knew it from him and called it a Leibniz rule. From this, we have a lesson. If you are making mistakes, if you are corrected, but if you rethink your mistakes and explain to everybody what is the proper thing, you will help a lot to people and also to your own career, because people know it as Leibniz rule. Okay, so after this history, let us see. LV is described algebraically. Look, what we have here is purely algebraic definition. So that's what we are looking for. We are looking for replacement of geometry. So these things are called derivations. So let me tell you a story. It happened 45 years ago. So when I was 14, we had a special class on advanced mathematics at school. And I had a teacher called Igor Gurvich. Who was actually not a teacher. He was so-called отказник. He was a Jew that tried to immigrate from Russia, but he was not allowed to immigrate. So he lost his job. So he came to our school as a part-time teacher. And he was teaching us advanced mathematics. So when he told us, look, what you think analysis is not a real thing. I will tell you a real thing. And he says that analysis is this. And at that time, when I was 14, I thought, oh, this is deep. I'm not ready to evaluate it. I was 14. But I feel that it is deep. Dear Igor Tomovich Gurvich, I thought, at some moment, I'll understand it. And actually, after thinking about it like 40 plus years, I realized that he was right. He put the wrong thing in my mind at a very early age. I had something to think about, and now I'm grateful. I cannot find him. I want to say him, thank you very much for bringing me a good taste of mathematics. By the way, in these talks, I am also trying to do similar things. I'm trying to give you the good taste of mathematics and physics. To my best. So these are derivations. So let us make immediate exercise. What derivations are? Consider the scheme. So it's my favorite scheme. It's a double point. And let us compute derivations for this scheme. It's an exercise, and making simplest exercise is, of course, a part of my task. So, what is D? First of all, let us check that D of 1 is always 0. How can I prove it?
So, sorry,
D,
not a double point, but 2 points.
At the moment, 2 points, but of course I'll consider later double point.
Sorry.
Let me tell you, it's a good question. In singularity theory, people consider singularity as the main thing. And when points go away, they consider it as a resolution of the singularity. So they consider the A equals 0 the main thing. They are not afraid to go to singularity, because singularity is a place where I'm telling you some philosophical thing. Singularity is a place where you have new phenomena, where everything is concentrated. All deep things are there at singularity, and not in the resolution. Okay, so let us compute this. Please help me. Let me compute D of 1 times 1. It's, of course, D of 1. Then let us apply the Leibniz rule. It is D of 1 times 1 plus 1 times D of 1. It is what?
Well, 0 plus 0.
No, we don't know that it is 0. It's how I'm going to prove it.
Well, then it's 2 times the D of 1.
Yes. So we see that D of 1 equals to 2 times D of 1. That's why D of 1 is 0. And here I can use any constant. Because when I say a map, of course I mean, sorry, I need to say linear map. Okay, this is our first result on derivations. Now, in this example, we need to compute D of x. Of course, okay? Because x squared is equivalent to a squared, to a constant. So derivations are determined by this D of x. Okay? What can we say about D of x? Let us compute D of x squared. This should be D of a squared. This should be 0. At the same time, this seems to be x times d of x, right? 2 times x times d of x. So now let us consider two cases separately. Case 1. A non-equal to 0. So what can we expect? What d of x could be? It could be alpha plus beta of x, right? Let us substitute. We don't know this alpha and beta yet. And we will get that 0 should be equal to 2x times alpha plus beta of x. So what can we conclude? It is 2 alpha x plus 2 beta x squared. Let us analyze. Could it be equal to 0? Equivalent to 0? Let us simplify. So x squared seems to be a squared. And this equals to 0 only if alpha is 0 and beta is 0. And you would say, oh, why should I do this calculation? It was obvious. These things are 2 points. What kind of vector fields can I have on points? Point is a manifold. Point is a smooth manifold. And of course, there are no vector fields. So we are not surprising that when A is not equal to 0, there are no derivations. Now, consider the case when A equals to 0. Then the second term disappears. And the only condition is alpha equals to 0. Great. So we conclude that all derivations have this form. We computed in real time the space of all derivations. They are not empty. So this space is not empty. So now we get some extra information about, in this case, this double point. It has derivations. And then you may start to think, oh, if it has derivations, if it has vector fields, it means that it could have dynamics, okay? And you may start to think along these lines. But this would be useful after we will get some ideas from the physics home. At the moment, being mathematicians, we just note that we have this interesting phenomenon. Now, let us play around this example. Consider interesting thing. C of x and the quotient by ideal generated by x to the n. So you may guess what derivations are. So may I ask you to guess? Or you see, Tim, may I ask you, you see, since you are the only one who represents West in this audience, and we don't have Yuan Yin among us. She mostly asks questions. So now I think it's time for you to ask questions. May I ask you to do this? So may I address my questions to you?
Sure, I guess.
Yes. So you see, because it means some special involvement, okay? So if you allow me, so of course I'll address to everybody. So everybody are welcome to answer questions, but I'll wait answer at least from Tim, okay? So please make a guess, like Leibniz did. What could be derivations here? Just a guess. I'm sorry. I'm sorry. I need to tell you some extra hint. If you have a derivations, you may check that they enjoy the following property. Geometrically. Suppose we have a vector field. You can multiply it by a function. It would be another vector field. It is clear. Now, algebraically. F of D. I consider composition. Multiplication by a function, okay? Element of the algebra, C times D. Claim, it is also a derivation. Let us check it. CD applied to A times B is C D of A times B plus C A dB. And now, here we use commutativity, by the way, that we can interchange C and A. It is CDA times B plus A CDB. You see, from this calculation, we see that derivations form a module over A. You see, it would help us in order to check if we get enough derivations. Whenever we have derivations, we can multiply it by an element of algebra and get a new derivation. So after this, let me ask, could you guess what are derivations of this scheme? I want you to give a wild guess, just to check your intuition. It could be wrong, but the first thing that comes to your mind.
Maybe by analogy with the last case, the last example, we'll have d of x to the n equal to 0, and all the d of x would be
what? Just, you see, if you make a mistake, it would help me, because you will show me how the normal people think about it. Because I'm kind of a specialist and I actually forgot how normal people are thinking about it. Okay? It is hard. It is a bit hard for me to understand what is easy and what is not easy. I'm sorry. So maybe somebody from the audience would give me, please pick up some derivation, and we will see. You don't need to bring all of them. Give me at least one of them.
The same answer as before.
Okay, d of x is x. So let us check. Okay, it's important to publish first. So now let us check. D applied to the x to the power p is what? Is of course x to the power p minus 1 p d of x, so conjectural, and with some coefficient. It's p x to the power p. So how should we check that it is a derivation? We would like to apply it to the product. But then you may say that this check goes exactly as in the case where there is no factorization. So it's really a derivation. Now, what is important? It's important that derivation should keep the factorization condition, namely d of x to the n should be equal to 0. So in this case, it is true, because if we put here n, we get n here, and the x to the n is equivalent to n. Okay? So, okay. Dongheng published first. So we have at least one. Do we have other candidates?
Well, beta of x, beta times x would also work.
Okay, well, it's clear that you can multiply by beta. Yes, but it's trivial.
I think it's up to the degree n minus 1 from degree 1 to n minus 1. All the coefficient can is free.
Of course. And of course, as you see, yes. So you may check that it is actually a derivation. Now,
but how is it linear?
it is C linear. It's a derivation. So it is linear. It is application of d on x. When I know d on x, I know d on anything. Because if d of x is this, then d of x squared is 2x d of x. And then I plug this thing here.
But shouldn't like d of 2x be equal to 2 times d of x? I mean this sort of linearity.
Of course, it's written linear map, of course. When I say d of x equals beta of x, it's what you think as a vector field. In the smooth language, you may say, let x be a coordinate. Let me take derivative along this coordinate multiplied by x and beta. And this is a vector field. You can say this for the smooth manifold. For the case of non-smooth manifold, there is no such thing as a d of x, d over dx. No. D of x equals beta is not a derivation. Let me explain you why. Because d of x to the power n, let me see, of n is 0, because x to the n, it's equivalent to 0, yes? From the Leibniz rule, it is n, x to the n minus 1 times d of x. Just imagine that d of x is beta. Then we will see that n times beta times x n minus 1 should belong to the ideal generated by x to the n. So it should be polynomial that starts with x to the n. N capital is not 0. This does not belong to this ideal. So beta has to be 0. But if we try to think what d over dx would be, we would say that it is something that takes x to 1. But it is not a derivation. So such thing does not exist on scheme. Interesting. However, there are a lot of derivations. Scheme does not have a coordinate that we used to have in smooth geometry. However, it has derivations, and they form a finite dimensional space of derivations.
I'm sorry, but I still don't quite get it. How is d of x equal to a polynomial in x a linear function? If I put 2x as the argument, it's not going to be equal to 2 times.
If you put, you see, I assume this, that d applied to 2x would be 2 everywhere. It's a linear function. You consider this x as an element of the linear space. So the algebra is, first of all, algebra is a linear space equipped with
I get it.
Associative cumulative multiplication. So when I say linear map, you see there is a notion, so-called field linear and a linear. So d of AB does not equal to AD of B. So would this happen, we would call it a linearity. So you can multiply. But we do not demand this. Derivations are different things. They are governed by the Leibniz rule. And it is quite a deep, and this is quite a deep statement, that we know what the vector fields are, while vector fields are not made out of vectors, if you wish. It's not that you have a family of vectors attached to points. It is something else. It's a new phenomenon. That's why we are discussing it. Moreover, in the case that we consider, derivations do not form a free module. Do you know what the free module is? Free module over algebra. Okay, let me remind you that module over the algebra A is a vector, is a linear space so elements from this I will call A, and elements from this I will call M, such that A could act on M. And this action is denoted, so pair A and M goes to what people used to call A at M. With an extra condition that A1, A2 applied to M is A1 times A2 applied to M. So this is a version of associativity. I don't know how people are teaching linear algebra in China, but in Russia, people decided that engineers and physicists should not know what the module is. They only teach linear spaces over fields. And they don't teach linear spaces over commutative algebras. Actually, they decided that engineers and physicists should not know what commutative algebra is in general. And it is a gap in Russian education. So may I ask, Sam, may I ask you?
Hello?
Sam.
Yes.
Sam, do you teach as the first course what the module is over commutative algebra in China?
No. And
You also don't know.
so we try to teach this as a representation theory.
Yes, but I mean at the very beginning. Okay.
Yes.
So,
But after abstract algebra.
so my position is that it is better to teach it at the very beginning.
Right.
Because later on, it's a fundamental notion. By the way, do you know why module is called module?
No, not really. Yes.
So the definition, the name module, very strange. Where do you see module here? It was introduced by Dedekind. And he was kind in a rush. And actually, what he studied Z over PZ, okay, residues. It was a ring. And in this ring, I mean numbers modulo IP, people understand that you can compare and identify things that differ by some number of p's, okay? And then he looked for an analog of the vector space. So he looked for an object such that this could act on it. It was Dedekind. And he had no idea how to call it. And you see, modulus originally from Latin means comparable. So he kept in mind that here n is comparable with m plus p. So he knew this being comparable in numbers, but he was looking for something being comparable in some abstract things that he was inventing. So he came to this notion of modulus, mean comparable, means that if you multiply it by a relation, you will still get a relation. So it's very bad name. But after the Dedekind, nobody renamed it. So please excuse this great mathematician for not giving a good name. So all students, when they come to modulus, ask why this object is called modulus. So it is actually a bad naming, okay? So this is a this is a modulus, or moduli. Okay. Now, so elements of the moduli could be acted upon by elements of the algebra. Now, if you have an algebra A, you can easily get a modulus that is called the free modulus, like A times E1 plus A times E2 plus etc. A times EK. It is something that we have in vector spaces. Okay? This thing is called free moduli. Free module. Okay. People forget about this modulus. Free module. And from this bad teaching of linear algebra at the beginning, students keep in mind that all modules are like this. Now we came to an example where module is not like this. Now, how can it be that module is not like this? Let us take an element and let us multiply it, and let us multiply it again, etc. Don't we get the full algebra A this way? And the answer is, we get it only if this A is not just an algebra, but a field, namely where all non-zero elements are invertible. And here we have non-zero elements that are not invertible. That's why the module that we get, the module of differentiations, is not free. So if you happen to come from mathematical school in Russia, or maybe from some analog in other countries, they teach you a lot about integer numbers. And then there, you know that that Z over Z2 form a moduli over Z. So you can multiply elements of this coset by any integer. But the fact that you can multiply over Z does not mean that it is free, because you cannot invert elements from the Z. because it's just a ring. But that's what they teach you at school. And when you go to university, they are telling you, these integers at school, just forget it. It was just for Olympics, just for fun. And they are teaching mathematics, forgetting this. And not giving definition of commutative algebra, I mean basic, and modules. And it's a pity. So I'm not criticizing you, my dear audience. I am criticizing professors, but not professors who were teaching you, because they were teaching you according to the program. I am criticizing the outdated professors who are writing these programs, okay? They have a great opportunity to teach you commutative algebra at the very beginning, but they are not doing it, okay? So mostly I am criticizing deans of mathematical departments, okay? You can tell it to your dean and he could come and discuss with me how to teach as a first year, how to teach linear algebra. Okay, I'm a bit angry on them. So you are victims. If you have problems here, it's because you are victims of wrong educational system, okay? So we discussed a bit about modules. We constructed these derivations. And now it's time to make a break. So now we have a 5 minutes break. But before break, let me ask immediate questions. If you don't have immediate questions, then maybe you'll have questions in 5 minutes. Actually, there is a logarithmic scale for asking questions. There are questions that you are asking. One group of questions you are asking in 1 minute, another group of questions in 5 or 10 minutes, another in 2 hours, another in 1 day, in 1 year, in 10 years. But if you have a question in 10 years, I cannot guarantee that I would be able to respond it due to life limitations, okay? So 5 minutes break. To write textbooks. Mostly they are involved in active research. Okay, so first university that will teach not commutative but supercommutative algebra would, I don't know, would get a prize of being innovative university. So let us see what could be the generalization of the notion of derivative. in supercommutative case. Let me remind you that in supercommutative case, an algebra A is Z2 graded. That means that A equals to A even plus A odd, and this plus is as linear spaces. And multiplication is such that A even times B even is, of course, B even times A even, A even times B odd is, and also this equals, and say M is even. A even times B odd is B odd A even, and this is odd. And A odd times B odd equals minus B odd A odd, and this element is even. Or equivalently, A times B equals minus 1 to the parity A times parity B multiplying by B times A. Where P is parity is called, and parity of A even is 0, parity of A odd is 1, and also parity of A times B equals parity of A plus parity of B mod 2. So I gave you two equivalent definitions. You may use the one that you like, okay? So now I'll define derivations. Derivation would be a map from A to itself linear, okay? there would be D even that map A even to A even and A odd to A odd, and also D odd that may map A even to A odd to A even. So these would be later called even derivations, and these would be later called odd derivations. Derivations have parity. So parity of derivation even is 0, parity of derivation odd is 1. And now the only axiom is D A B equals to D A times B plus minus 1 to what? Parity of D, parity of A D B. So mnemonically, it means that I am somehow moving this D around A. And that's why I get this sign. Okay? Let us consider examples. Consider the following algebra. That sometimes people call algebra of skew polynomials. Or external algebra. These two names come because of different intuition that people have. Actually, it means that it consists of, it's spanned by monomials on theta. That is antisymmetric if we interchange them. With this example, C of theta 1, theta 2 is a span of complex numbers. Okay, so I will put here 1, theta 1, theta 2, and theta 1, theta 2. And I assume here I assume that theta I, theta j equals -1 theta j, theta I. So this was first discovered by Grassmann in the middle of the 19th century. Let me remind you from this, you automatically get that theta I squares to 0. I think it's clear how to multiply elements here. You just multiply, and if you have two thetas, it is 0. If you have theta 2, theta 1, like theta 2, theta 1 equals just minus theta 1, theta 2. So this is a supercommutative algebra. Let me ask you, what is the A even of this algebra? It is span of what? Who will answer?
Of 1 and the product of theta 1 and theta 2.
Thank you, Tim. And what is A odd? What? And now I'm waiting for a reply from Chinese side.
Theta 1
come on.
and theta 2.
Very good. Great. Now it's time to find derivations. So, Dong Hang, sorry. You are great in finding derivations. Could you tell me what are the derivations here? Could you tell me what are the even derivations? Maybe Tim could say.
Well,
Let
I
us
guess
find
it should be
even.
a linear combination of thetas.
Okay, so first of all, D even on 1 should be what?
No, 0 by the previous arguments.
Great. Then D even on theta 1. What would it be?
It should be linear combination of 1 and theta. Oh, no.
What?
Theta 1 and theta 2.
Okay, great. Alpha theta 1 plus beta theta 2. And what could we say about D even on theta 1, theta 2? Could we, so what could it be? It should be
Any
something
element of
even.
A even?
So it should be an even. What could it be?
Any element of A even?
No, you see, when we describe derivations, we describe them on the basic elements. So what would be D even of theta 1, theta 2? From this formula.
Alpha theta 1, theta 2.
So
The beta term is 0 and
we cannot do it yet. because we have not described the d even on theta 2.
Yeah. We should prescribe.
So d even on theta 2, let me call it alpha, beta, gamma, theta 1 plus delta, theta 2. Now, what is d even on theta 1, theta 2? So who would start?
It's alpha theta 1 theta 2 minus
Theta 2.
Delta.
And then plus.
plus,
Because
yes.
it's 0.
Yeah.
Gamma theta 1 plus delta theta 2. So what is it?
Alpha plus delta theta 1 theta 2.
Yes, so it's, and here we have 0, and here what would we, and what do we have here?
Delta.
Plus delta theta 1, theta 2. Let me check. With the sign plus, yes? Isn't it interesting? So this is alpha plus delta, theta 1, theta 2. If we consider this as a matrix, what is alpha plus delta?
Trace.
Trace. So you may think why trace appears here. Is it coincidence? You see, you may think about it and consider other examples. But at the moment,
If we
let me
multiply
consider-
those things,
what?
if we multiply those two lines, we get the determinant of this matrix times theta 1, theta 2. And the
however,
trace is connected with the derivative of the determinant.
Yes, but trace is connected with the derivative of the determinant, and derivation, being a vector field, is connected to diffeomorphism. Okay. So as a homework, you might try to rethink why it happens. So I assume that you know that that if you have not derivation, but a linear map, then, okay, let me give you a hint. Anyway, it's in the program. So suppose I have this external algebra. And now I'll have not derivation, but the full linear map L. That takes theta I into Lij theta j. Then I can induce the action on the full algebra according to the rule, not Leibniz, but old Leibniz. So that is something that we will call diffeomorphism that we described, yes? So there are some maps that preserve multiplication. You see? So it is not about, it's not the Leibniz rule. It's the full diffeomorphism. Now, consider L applied to theta 1, theta d. It would be some number. Right? And this number is called determinant. And this is the mathematical definition of what determinant is. You are not talking about matrices and permutations. All these permutations are hidden in the definition of the algebra. You just know that linear map preserves degree in thetas. And you also know that there is only one element of the top degree in thetas. It is this product. That's why the action of L should be multiplication by a number. And this number is determinant. Now, you may think, how diffeomorphisms are connected with vector fields. In smooth geometry, we say that vector field could be exponentiated to diffeomorphism. So how do we do it in smooth geometry?
So,
we calculate integral curves. And do something else. But it is smooth geometry.
so in this case, is this trace some kind of Lie derivative?
So from the linear algebra, we know, at least you should know, the formula. So it doesn't matter how they were teaching you. Determinants Determinant of 1 plus TL is 1 plus what? Plus T times trace of L plus O of T squared. Do you know this formula? So Tim, you know it, yes? Dong Hang, do you know this formula?
Yeah, yes.
Okay. So we know what determinant is. So now you may try to guess why trace appeared here.
So that I guess the even derivation is infinitesimal automorphism of the
Great.
or endomorphism of the
Yes.
algebra.
Yes. So this is the meaning of. Thank you. You see, it's good if you know, but if you know something, it's not because of me, it's because of other professors. But if you realize something during my talk, so it is evaluation of my work. I really want you not to memorize things. I really want you to understand something new during my talk. So, e to the d of d even seems to be automorphism of the algebra. Especially when superalgebra is finite dimensional. Okay? So I think I gave you enough hints to understand why do we have a trace here. Okay? So here we have the first exercise in derivations. Now, it's interesting that there are not only even derivations, but also odd derivations. You see, we started with this example. Now, what can we say about odd? What should we write here? Hmm?
probably both of them should be some elements of A even.
Yes. But
So it's like alpha.
now we have very definite algebra. 1, theta 1, theta 2. So what we can write here?
Alpha plus beta times theta 1, theta 2.
Great. What we can write here? Similarly, yes?
Yeah.
So while we are writing this, let me ask you, is what I am telling you simple? Okay. Is it simple? Is it doable?
Yes.
Okay. So now let us compute what would be this d odd applied to theta 1, theta 2. Alpha plus beta theta 1, theta 2 times theta 2 plus theta 1 times gamma plus delta theta 1, theta 2. All right?
Why plus? Shouldn't it be minus?
So you are right. It should be minus. So it's alpha theta 2 minus gamma theta 1. So here I cannot play these nice games about determinants. Okay? However, here I can here I want to tell you that I forgot to tell you one thing about derivations. Okay? That was very general. It was my mistake. Please forgive me. Let me do it in an opposite way. Please tell me what fundamental fact about derivations I should tell you that I forgot to tell. So I told you that derivations form a module over an algebra, it's okay. But what is so important about derivations? That we know in the smooth case, and we have to check in the abstract case. And I forgot to tell you about it.
Maybe that the commutator of two derivations is also a derivation.
Great. Great. Yes. So I forgot to tell you this fundamental fact, that when you have a derivation of the algebra, two derivations, then d2, d1 minus d1, d2 is again a derivation. Who was the first man who realized it? What was his name? At least what was his family name? Okay, his first name was Sophus.
No, that's Lee.
Yes? It is how Sophus Lee came to the notion of Lie algebra. He was studying vector fields. So let us get an algebraic proof of this statement. Let us compute this. Now I apply the 2. So it is kind of lengthy calculation. It has a lot of terms. And what do we see here? We see that here we do have Leibniz rule. But here are terms that it's not what we want. Right? Now, what if we interchange 1 and 2 and take it with minus sign? Do you see that these terms cancel? Okay. At least I see that Tim nods his head. So Dong Han
Yes, the
show
middle term.
himself. So he has to say something. Yeah. Yes, they cancel. So it is a purely algebraic fact. Okay? So there is a new operation, anti-symmetric, discovered by Lie. By the way, have you heard about Jacobi identities? Yes. So once again, Tim, who is not afraid to show up, nods and Don Hank has to say that he heard about Jacobi identities.
Of course.
Of course. So can we prove it from this? So how to get that this operation satisfies Jacobi identity?
Any commutator automatically satisfy the Jacobi identity.
Yes, but so any, you are right, any anti-commutator of operators due to associativity satisfy Jacobi identity.
Yes.
Yes. So it means several things. First, that even differentiations form a Lie algebra. But now we have odd things. So we automatically come to the notion of the super Lie algebra or super algebra Lie. So when I'm explaining it like this, you may think, how could it be that super algebras, super Lie algebras were discovered only in the 60s? While it is so obvious. What?
Who discovered this?
I think it was Berezin, but because Berezin started to think, Berezin started to follow Grassmann. So if you look at Bourbaki, they are not studying supercommutative algebras. It's interesting. They had a lot of external algebras in their constructions. I mean the French homological algebra, but somehow they missed it. I don't know. So they actually, Bourbaki group, actually missed superalgebra. So it was Berezin who followed Grassmann, who was a Frenchman, by the way. And discovered it. So I think that in this way presenting things, it's obvious, okay? It's obvious that you could not study one without another. These things are very close and very natural, okay? So if you have superalgebra as a replacement of the algebra of function, then you have superalgebra Lie of super differentiations. And of course you put proper, you put minus signs at proper places, right? Oh, it's a time for the break. So I hope that I'm not going too fast. Maybe I'm going too slow, but I'm trying to keep the audience. So what I actually don't like, I actually see two active participants, like Tim, who represents West, and Dong Han, who represents East, while other people are passive. I don't see them, I don't hear them. Maybe they are robots, but if they are robots, they are outdated robots. Now, in order to imitate your presence, you need to have a robot with artificial intelligence that says something sporadically, asks questions, you know. It's a technology. Okay. Okay. Do you have questions, comments, immediate questions, comments, etc.?
So what was the interpretation of the odd derivation?
We will come to this. It's a good question. We will come to this in 5 minutes. And actually, I would like to tell you that there are questions. What is the proper interpretation? Okay? So I consider this issue as being semi-open. And I'll explain it as later, okay?
Okay.
But was it understandable? Tim, thank you. How do you think, Tim, is the speed proper? Or I should go fast or
Maybe you
slower?
can go a little bit faster.
But so please excuse me. I'm going this slow. I'm trying to keep the audience. But I hear your comment. I hear your comment. So please excuse me for being too slow. Okay? You know that I can go faster, but I don't want to go faster. Sorry. Actually, I'm telling rather deep things that you could not read in a standard textbook. So that's why I want, so I am keeping the speed so you could have time, not just to multiply two monomials, but to think what actually is going on. Okay? So let us have a 5-minute break. So several interesting issues. And we see that at a moment, we came to the notion superalgebraically together with the notion of algebraically, right? And of course, you will see that in superalgebra, you have supercommutator. That is D1 supercommutator D2 is what? Is D1 D2 minus, and here we have this correction, parity of D1, parity of D2, D2 D1. Okay? Well, and now let me tell you something interesting. Namely, here we have, interestingly, homological algebra as a particular case of superalgebra. So nobody treats it like this. What is interesting here is that if superderivations D1 and D2 are odd, okay? Let me put here odd. Then the sign here is actually -1 minus is plus. And therefore, this is called anti-commutator. And therefore, it is interesting to consider a single derivation that is odd. Single odd derivation. Let me call it D odd. And it's anti-commutator with itself. You see, its even counterpart is trivial. That's why we never saw it before in the conventional commutative algebra and geometry. And here, we have an interesting thing. This equals some D tilde even. Okay? And do you know how this algebra is called in modern physics? It is known as supersymmetry. As great Sophus Lee mentioned, we may consider not all vector fields, but we may consider vector fields that preserve something. Okay? So now I'm coming back to Sophus-Lee theorem. So this Lee considered subalgebra of derivation preserving something. Okay? You may ask, what does it mean, derivations preserving something? You may consider D that preserves A naught. So may I ask you to interpret this in geometrical terms? What does it mean that D applied to A naught is 0 if A naught is a function? So on algebraic side, it's clear. Vector field preserves function. But functions correspond to geometrical objects. Okay, so for advanced group of the audience, you may think, what does it mean? What I would like to mention is that if D preserves A naught, then the commutator also preserves A naught. That's why Sophus-Lee, when he discovered his algebra, was actually thinking not about abstract algebra. He was thinking about algebra of symmetries. Okay? So he just abstracted the notion from algebra of symmetries. He abstracted the notion of Lie algebra. And of course, he applied it to theoretical mechanics, but we will come to this on the physics hall. Okay, so preserving something. And now I need to tell you in advance that here we get it from nothing, from abstract mathematics, the superalgebra of symmetries. And this superalgebra of symmetries is realized in models of theoretical physics, in the concept of supersymmetry. This was understood by Russian physicists Golfand and Lichtman. So actually, the person who discovered supersymmetry was Golfand. And Lichtman was his student. Okay. Now we already see that we have an interesting algebra, interesting super algebra. And now let me consider a particular case of this. Imagine that this d tilde equals to 0, suppose. So then we are coming to the very fundamental notion of d odd, such that it squares to 0 is called a homological vector field. You may ask, why we calling this vector field homological? What it has to do with homology? And the answer is that people found interesting examples of this d odd that squares to 0 in different fields in mathematics. And they called not this, but particular cases homological algebra. So I'm telling you something deep. Namely, I'm telling you that homological algebra, that is the greatest discovery of French mathematical school in the middle of the last century, from this point of view, should be considered as a particular case. Okay? So now let us see what people call homological algebra. Okay? Homological algebra comes as follows. Suppose you have d odd that is linear in some coordinates. When I say, so before, there were no coordinates involved, okay? The only structure was Z2 grading. But here, we say that d odd is linear in some coordinates. So you may ask, what does it mean, linear in some coordinates? It actually means that how to say that the algebra that we study is actually, say, complex numbers and here are some x's that I will call even coordinates. There are thetas that I call odd coordinates. And d odd applied to x equals something proportional to theta, and d odd applied to theta equals something proportional to x. D I alpha theta alpha, D alpha I xi. And then you can tell me, wow, how it could be? The total structure was very nonlinear. There was no notion of coordinates. Moreover, we already studied example where there was no coordinates at all. And I am coming back to a system with coordinates. But only if you make such specialization, you will get the notion of homological algebra. Because then you may introduce, in this case, you may introduce the vector space V that is a span of, xi's theta alphas, okay? And D odd takes V into V, it means that it is linear, okay? And considered as a map from V to V, it is called D. And condition is D squared equals to 0. And this is homological algebra. Such space V is called complex. D is called differential. Elements of V such that dV equal to 0 are called closed. Elements of V such that V are D of W are called exact. Okay? And the homology of D of the complex V is the space of closed factor by exact. So most probably you heard this definition. Okay? I am pretty sure you did. But I am not sure that you realized that this definition is very particular case of the construction that I explained to you. And if you take any book on homological algebra, you would read there that homological algebra is a category whose objects are complexes. So these are pairs VD whose morphisms are linear maps. And being linear maps, so it's a category, yes? And what is important that morphisms have morphisms are complexes themselves. Do you know why? Do you understand why they are complexes? They inherit the structure of differential from the differentials that are acting on each particular complex. Suppose there is a morphism. Now we can add D, we can define D, let me call it adj. Adj means adjoint on M as follows. D edge on M, it should be a morphism applied to V1 okay, it's better to write it not in a section, is just first you do this and then you do this. Okay? So all this complicated science that is called homological algebra is only about this category. I may show you a book. I don't know, you may open Bourbaki if you wish. They had a book called homological algebra. So that's what they are studying. Okay? Now, how this is related with the new notion of supermanifold equipped with homological vector field. So there is another name. Is also called Q manifold. So how this homological algebra is related to the theory of Q manifolds? Homological algebra is just linearization of the category of Q manifolds. And it's a thing that Bourbaki and Grothendieck never realized. So I told you before that Russian school missed homological vector field. French school missed supermanifold structure. Putting things together gives you a modern knowledge. Modern knowledge is the notion of Q manifold. And here, let me consider the main example, okay, of Q manifold. That was missed by, I think it was missed, yes. I will come to geometrical Q manifolds later, but now let me consider something not very naive, but more interesting. Consider again external algebra, theta 1, theta k, okay? Let us try to write down d odd explicitly. So we need to write d odd on theta I. So what could we write here? Could you dictate me what to write? This has to be even. So suppose I don't want to have constants here for some reason. So what should I write? Some f, okay, let me put it, the index up. So fi j1, j2, theta j1, theta j2, plus, what should I write there? Tim, could you read me?
Well, fi j1, j2, j3, j4, and the product of 4 thetas.
Plus, etc. Good. And then, what is the condition of homologicity? Mhm. So could you guess what would be conditions for f with 2 indices, for f with 4 indices, etc.? First of all, let me call this thing f2 because it is a binary operation. Let me call this f4, etc. So when I consider d squared, what types of terms would I get? I would get some structure that is quadratic in f2, right? Let me call it x22, but temporarily. Then I'll have some structure that would involve f2 and f4. Then I will get some structure that would involve f2, f4, f6, and I need to group it with the structure 4, 4. And so on. Okay? So could you guess before computing what is the meaning of x22? So what is this important quadratic equation that we are getting from homologicity condition?
Jacobi identity.
Oh, don't know. So Tim, do you know this? Do you want to say that you never thought about it?
I don't think I have.
So let it be an exercise. Compute this, and check that this is Jacobi identity. But now, note that this Jacobi identity do not come alone. There are other operations that satisfy other equations. So isn't it interesting that following ideas of Sophus Lie, we are coming not only to Lie algebras, but to some higher structures. And then let me incorporate here also x's And I'll call these guys all together by letter C. Okay? So CA. So parity of CA could be either 0 or 1, of course. Then I will have no restriction on degrees. Okay? Then I'll write D odd on, now on CA would be, please, now Tim, just tell me what to write. How should I start this? F, sorry, FAB, CB plus FA, B1, B2, CB1, CB2, plus etc. All right? And then I'll have a lot of equations on F's. Tim, do you know how these equations on F's are called?
No.
No. Maybe Donghan, do you know how these equations on F's are called?
Is this? I don't know.
Okay, so these equations are called L infinity algebra. So now I want to ask everybody to make an exercise, namely to compute these equations and try to interpret them. Okay? It is interesting, you see, here is some structure that looks deeper than the structure of Lie algebra and maybe even super Lie algebra. And please write me or send me the page where you computed and understood these equations. So you have to compute them yourself. You have to think about them. Okay? And after you do this, we will discuss their meaning. Okay? When you get some experience, we will discuss their meaning together. But right now, I'm telling you that what happens here is like general covariance versus special covariance of homological algebra. That's how the structure appears. You see, I'm trying to be a mathematician right now. I'm trying to give you only mathematical motivations. So when two horns of my course would come together, I will add the motivations from physics. But at the moment, I do not expect that you know proper physics. I need to talk a bit about physics. And then you will get also view from theoretical physics on what happens. Right now, what I'm just telling you is that when we go from linear transformation to general transformation, in physics, it's called general relativity. So when you have linear transformation, in physics, it's called special relativity. So homological algebra is a special relativity. Theory of Q manifolds is a general relativity. And if you think that you can read it in some books, not attending to this course, you are wrong. So please come, get novel view on mathematics and physics, ask questions, do homework, okay? So that's it for today. So now comments, questions.
What about homological algebra?
Homological algebra. So conventional homological algebra. It's a linearization, of course. You should compare two categories. Here you have theory of maps between manifolds, or equivalently maps between superalgebras. Not superalgebras, but superalgebras. Then you can consider linearization of it and have map. So derivative is a map of tangent spaces. What you have here is homological algebra. And what you have here is the theory of Q manifolds. So I am just trying to tell you that all this homological algebra is a kind of linearization. Like you know that, okay, still I assume that you know something about physics. You know, so when I hit a body, I have a vibration. Vibration could be understood as oscillators. Oscillators are governed by the linear algebra, okay? So all small movements are governed by the linear algebra, the algebra of small fluctuations. But there are more serious motions that are not just linear algebra. So oscillator is a piece of physics. You may ask, is it possible to understand physics if you know only oscillator? I would say I doubt it. If you know physics, you may understand oscillator. You may consider oscillator as an example of physics. But you cannot reduce physics to oscillator. Okay? So this is the relation between homological algebra and theory of Q-manifolds.
So the tangent space is the space of the derivations.
So you might see that if you you need to do this exercise. If you do this exercise, you will see that the linear term here, this term, is a differential. And then you will try to understand what are the higher terms.
So only the linear term is homological algebra.
Or, okay, only this, or you may try to embed the full thing inside homological algebra, but it would be just a particular case. In some sense, it would be kind of, let me try to give you an analogy. So another analogy is like this. Suppose you would like to understand manifolds, okay? You may try to understand manifolds by embedding them in C to the n and take all concepts from C to the n. It's called external geometry. But there is also internal geometry. So this is theory of Q-manifold is internal geometry. Homological algebra is something like external geometry. That is weaker, but easier to understand. In geometry, people first understood external geometry, like sphere in R3. And only later they realized that the proper way to study is internal geometry. Here, the same thing happens. So you see, not only I am trying to tell you that standard point of view on homological algebra and on commutative algebra is outdated. I'm trying to explain it to you in the simplest examples. And that's why I was explaining all this very slowly, okay? You see, structure of this course is not that you can just pick something from one place, go to the internet, pick something from another place, and then somehow put everything together. You cannot do it because philosophy in mathematics is changing. And you could not take something from one philosophy, something from another philosophy, okay? So philosophy, if you wish, of Q-manifolds is something that replaces philosophy of commutative algebra and homological algebra. Commutative algebra itself and homological algebra as two separate volumes of Bourbaki are outdated because they are 60 years old, 65 years old. And I'm telling you the new approach. And not I'm just speculating. I am just inviting you to see why it is like this. Moreover, if you want to discuss with me, you may attack any arguments, but not in the way that in the book written by great mathematicians, it is said like this. No, we have very definite constructions, definitions, examples. If you find something non-natural here, please tell me. Okay?
Okay.
So I just want to say that people like Kontsevich, of course, are using it or keeping it in mind. So Kontsevich is very lazy to write books. Okay? He is even lazy to write articles himself.
I'm sorry. I have to leave. Someone waiting for me.
Yes. Oh, okay.
Sorry.
So please.
Sorry about
So let us quit. So let us quit, save recordings, and send me the links. Okay.
Okay.
Thank you. Thank you,
bye.
Tom Frank. And
Thank you.
But still, maybe there are some questions or comments, or you are also welcome to write me. We can have a private discussions.
Okay.
During office, don't hang. We will meet on Saturday, yes?
Yes, of course. Yes.
As a fixed time. Okay.
Okay.
So you
okay,
can go. You can go to more advanced parts, like discussions on BV or like discussions with Dong Heng on A infinity.
Yeah. I'm
So
interested
that
in A infinity.
Sorry? On A infinity and
yes.
L infinity.
Yes.
And we will continue with you. Okay. You have to go. Thank you.
Yeah, thank you. See you.
So any questions? I really wanted to surprise you. So Tim, so did I surprise you? Honestly.
Well, the part about the differential being connected with this odd derivation, yeah, I didn't expect that.
Okay. Do you know that the title of the course is Ideas and Surprises? So I actually wanted to have some surprises. So actually, I promise from now, I promise to keep at least one surprise during the talk. And if it will happen that I will not surprise, then to be my debt. It means that next time I will need to give you 2 surprises. Okay? So number of surprises should be at least higher than the number of talks. Okay? But you know, I always have ideas. So have you heard new ideas? I mean, ideas that are new to you. Yes. So I fulfill my obligations. You know, I promised ideas and surprises. I am giving them. Yes, and I also promised simple examples. Were examples simple enough? Yes. Okay. That's it. See you next time. I'll write you different kind of letters with references, extra literature, etc. Okay. Goodbye.